我知道你是会玩的，但是没想到这样会玩。吧？阿姨的，你要什么是阿姨？对。啊，我知道 UN，知道就是这个句嘛。哦，我印象中是 PUA，啊，不是那个，不是那个 OK，医生，好像什么是 RUA 过去，比较早。definition，他们用那个 run 那个东西，听过 run 那个球呢？听过 run，球，对，真是的。最初那一次应该是 China。呀，对。我早应该没有那个。你知道我事情过那些吗？对 ，run 那次还有很多。不是，那也对。炸裂，炸裂，炸裂，炸裂。好，我们今天上 run，但是没有想到就会。太炸裂了，这样我就比较明白了。你饭还没吃吧？没事没事，慢慢吃慢慢吃。我的课准备一定很下饭。对啊，在 Google Map 显示 LY5是电个圆筒数式。人去 Google Map 搞事情。不知道啊，那我会骗出来。Hey, today a bit relax a bit, not so rigorous. You guys got exam, right? Yeah, we just briefly say some important theorem and then discuss through how to prove. Okay. So where did we left yesterday? So yesterday we start with a function. Okay. And okay, let's start with the easiest function first. So we start with a straight line function. Let's say y equals to mx plus c. Hello, hello. Y equal to mx plus c, and then what did we discover yesterday for this kind of function? Yeah, the gradient. The gradient is what? The gradient is m. And then what does this gradient represent? You take any 2 points on the curve, on the line, and then you compute the ratio of y difference, yes, y1 minus y2, and divided by the x difference, x1 minus x2 is always the same everywhere. Okay, no matter how far you go, no matter where you pick this y1, y2, and x1, x2 on this curve, you always get the same m. Okay, so I mean, to be precise, we make our y into a function or in x, then you will see this as f of y1 to be f of x1, y2 to be f of x2. So you will see something like fx1 minus fx2 over x1 minus x2. Okay, so this is a special of this line. This is a, how to say, invariant, doesn't change one. Okay, no matter which 2 points you pick on this curve, this m won't change. Okay, we call it the gradient. But life is not so easy, right? So why is it not so easy? Because your function doesn't always look straight. Okay, your function maybe looks something like this. It's like uphill, downhill, right? Your life is like uphill, downhill. Suddenly you're very happy. I got Hai Di Lao. And then after Hai Di Lao, anomaly, yeah. or stomach ache.
我要减肥。
我减肥。我觉得你在内行。Okay, it's okay. Okay, joking. Joking. Okay. So I mean, yeah, go uphill and downhill. So how do we decide all these gradient or all these points? Okay, how do we decide, for example, gradient at this top here? How we decide this? Similarly, we still do the same thing, right? We take nearby points and then we compute the ratio, change in y and change in x. Okay, we compute the ratio. But you see, if we take different nearby point, this gradient will change. Okay, this gradient will change. Okay, when you take different nearby point. And then if you take more nearby point closer to the original point, what happened? You are taking a limit. Okay, so you are taking a limit of x going to let's call this S0 of the ratio of the secant. We call this a secant. Okay, we call this ratio to be a secant, and then of fx minus fx0 over x minus x. Secant is just the ratio of the y difference and x difference. So yeah, I just define like that. Let's call this quotient as a secant. Yes. Tangent is the tangent secant one. So secant is what? What's the precise definition for secant here? That one, yes. Wait, let me think. What is cos? Okay, let's try and reconstruct that argument. So cos theta is what? Cos theta is adjacent over hypotenuse. Adjacent over hypotenuse. So if in that sense, secant is hypotenuse over adjacent. Hypotenuse over adjacent. Does it make sense also? I think it's just okay. Just let me check the secant correct definition. Ratio of the hypotenuse to the shortest side. See, okay, secant here is just a straight line cutting a curve at 2 or more points. That's all. Okay, not the 1 over cos secant. Okay, yeah, just a straight line cutting two or more point. So here, there's 2 points here. You cut every straight line. We call it secant. And then here we also take 2 points and then we cut it as a straight line. We call it secant. Okay, so we take the limit of this ratio. So yesterday, I think Jack put out a very good argument here, right? So I mean, good point, not argument, good point here. So if you make x to be S0, right, then you will get 0 over 0. This thing is like undefined. Okay, so we are not interested in this value here. What we are interested is the limit of this function. Okay, and yesterday I showed you that this limit will converge to something interesting. Okay, for example, in x squared. Okay, if you compute, for example, let us compute what's the limit for x squared. So at a random x of fx x squared, what's this limit here? So converge to where? Converge to some places. Okay. So let's say at this point, and then of fx minus fx naught over x minus x naught. Okay, what do we get here? We get x squared minus x naught squared over x minus x naught. And then from here, what do we get? We get x naught. We get x plus x naught, right? Get cancelled out. Okay, and then altogether we get 2x naught. Okay, so we get something useful here, 2x naught. Okay, it's not 0 over 0. What's this 2x naught? This is the gradient at that point. No? When you differentiate 2x squared, what do you get? 2x, no? 2x at every x. Okay, does that make sense? So it's this 2x here is a function with point. Correct or not? Function with point. This is a function with point. So let me draw to you. For example, this is x squared, right? Okay, if you want to consider a gradient, okay, a gradient or a secant, the limit of secant at this x0, x equals 0, what do you get? The gradient here is really 0 because 2x0 when x0 is 0 is 0. Okay, and then what else? If x equals to 2, fx equals to 4, right? Then what's the gradient of this line? What's the gradient of this line? 2 times 2, which is 4. Okay. So this limit here is a function of points, a function of your domain. So how do we define this limit here? Well, what do we say if this limit exists? What can we say about this function if this limit exists? Huh? More important than continuous. So differentiable. Okay, so we say that. So on df. Okay, and then let x be limit point. Yeah. Okay. So we said that f is differentiable. F is differentiable x if what? If what? What did we say yesterday? If the limit of the nearby sequence secant exists. Okay? If this number here exists. Okay or not? So for fx equal to s squared, this limit exists, which is 2x. Okay, 2x. And then we call this and then we will denote. So this is we will denote this number, okay, this limit here. So let's say equal L, and then we will denote L by f prime of x naught. Okay, f prime of x naught. There are a few ways we write this, right? Remember in your calculus, what way we can write this? What other way? D over dx, right? Fx evaluated at x naught, for example. Right. You also have df dx also can. What else? Sometimes you will put dy dx, right? Dy dx. And then I think that's it. Yeah, that's it. Okay. So these are different ways to write it. And then what do we call this number here? What do we call this number here? What do we call this number? F prime. What's the name for f prime? Sorry, derivatives. Yes. So we say that L is the derivative of f. Yes. Try to connect everything you learn in calculus. Okay, so we are building on foundation. Okay, we are building on this foundation. Okay. Yeah. Okay or not? And then what's that line? What's the secant line that we found there? What do we call it? Tangent line. Okay, gradient is just the M. The line, we call it a tangent line. Okay, good. So let me put here. So for so the line y equals to fx naught plus f prime s naught times x minus x naught. Okay, for all x is the tangent line. Okay, tangent line to the graph. At the point, no, fx naught. Okay, so here, so what's the tangent line of our original function here? Let's say we pick S2. What's the tangent line at S2? What's the tangent line here? Is the original curve, okay, because it's also having the same gradient. How about the tangent line on S1? Also the same curve. So you see, the tangent line at every point coincide with the original curve here. Okay, so you can somehow like use tangent line to build your curve back. Okay. How about this? What's the tangent line on S0? The horizontal line. Horizontal line. Not just y equals 0, right? It has some shift. It gets shifted up, right? It shifted up. But the gradient is 0. Okay. And how do you get this tangent line here? You consider the limit of the nearby secant. Okay. So you can see that actually, you see the sequence here. Can you imagine that this sequence can be realized as some tangent line? Can or not? Can realize this nearby sequence as some tangent line or not? You see, if I take this line here, okay, I mean take this line, okay, let me move it. This line, I move it, okay. I can move. This become a tangent line of some nearby point. And then what else? I can move some M2, the tangent line with M2. I can move this one also. Then I can realize this tangent line, this secant as some tangent line. And then M3, I also can move a bit and realize it as a some tangent line. Okay, so you can see, I can use this tangent line to somehow reconstruct this part of curve. Does it make sense? Make sense or not? So in more abstract mathematics, when we study curve, right, we don't just study the original curve. What we study is we study the tangent space. Because from tangent space, we can construct the curve back. Because sometimes tangent space has a easier property to study. For example, maybe tangent space is a vector space, but our manifold is not a vector space. Sometimes, most probably. Okay, so tangent space has vector space, then we can use linear algebra to study vector space. Okay, tangent space, for example. Okay, later we will learn a theorem that this sequence can be realized as some tangent line. Okay, not sure it's today or next time. Okay, so right, so let's do some example. Okay, let's do some example to confirm this definition here. Okay, So for example, let's repeat again. So in calculus, right, you know that, you know what? What did you know? You know that this kind of function have derivative fx, f prime x equals to m for all x. So you need to tell me, you need to ask me, right, where this where this f is defined. Okay, this f is defined for all r. Okay, so how we prove this? How do we prove this? F prime x equals to m. We need to compute the limit of the secant. Okay, we compute the limit of the secant. So how do we compute the limit of the secant? So if it is true for all x, then we just start with a random x. So let's just fix some x in R. Then what? Then we can take a limit of y to x, and then fy minus fx over y minus x equals to my plus b. So limit of y to x, my plus b minus mx plus b bracket. All right, bracket is very important here. And then y minus x. And then what do we get here? So the b and b cancel. And then you can factorize out the m, where you get y minus x over y minus x. So really, you just get the limit of m. But m is a constant. Okay, so maybe we need to fix, should we fix the constant here? Is it clear that this is a constant? Okay, so to be precise, we should say that for m in R, so we are fixing a constant. Okay, we define a function from R to R, which is mx plus b. So here we get m. Okay, so this matches up with what you learned in calculus. Okay, actually, I remember this definition, I think we, at least for me, I also see it in SPM. They did it, right? So, but just that they don't use it only. I think they don't even teach, for my class, they don't even teach the concept. They just show like some very gigantic limit definition, but they never do it. I think they call it the first principle. If you go back to your SPM textbook. I cannot speak for UEC, I don't take UEC. Yeah, they call it a first principle. Okay, so in this course, everything we do with differentiation, we will use first principle here. Okay. Right. Okay, so maybe we do one non-example, right? Let's do one non-example. So this is a very famous function here, the absolute value function. So let's define f from R to R such that x is equal to the absolute value of x. You know what's this function defined? How is this function defined? Equal to x if x is greater than 0 and minus x if x is less than or equal to 0. Okay, so for this function, remember we proved that this function is continuous. Okay, last time we proved that. So last time we proved that this function is continuous. Okay, if you forgot, please exercise again. Okay, you need to exercise. It's like people do gym. Okay, you every day, if you want to do deadlift, you have to deadlift every day. Okay, you cannot say today I done deadlift, tomorrow I don't do. Okay, you cannot train one. So if you want to train in maths, also you have to do similar thing over and over and over. Okay, so you try and prove whether this function is continuous using sequential continuity or using epsilon delta. Okay, try both. Okay, then you will gain some experience in it. So last time I proved that this is continuous everywhere, actually. Okay, but this function is not differentiable at one point. Which point is it not differentiable? Okay, so we claim here this function is not differentiable at 0. Okay, so before proving it, I state this statement here, not differentiable at 0. So based on the definition of differentiability, what you should think? What can you think? Negate differentiable. So how you negate the differentiability? Sorry? What doesn't exist? What doesn't exist? Huh? What doesn't exist? The limit doesn't exist. The limit of what doesn't exist? The limit of the secant doesn't exist. Okay, so you need to prove that the limit of the secant doesn't exist here. So how to prove the limit of the secant doesn't exist? So meaning it should converge to two things maybe. Right? You need to find two subsequence that converge to two things to show something is not converging. This is one way, right? Or you show that it diverges, the limit diverges, right? There are a few ways, right? Last time we learned. So how? Yeah, so you want to show the limit diverge or you want to show the limit doesn't converge? Okay, how to show a limit doesn't converge? If if a limit if a sequence converge, right, then all the subsequence must converge. So if you can find subsequence that doesn't converge to the same thing, then the sequence also doesn't converge. Okay, so can you find two subsequence that take different limit? Think about it. Not too hard. Yeah, you can talk to each other. Huh? I mean, one way you can think of this graph, right? How does this graph look like? Okay, this function look like this. So what are the, how does the tangent line look like on the right hand side, left hand side? How does the tangent line look like on the left hand side? Straight, what do you mean straight? Is this curve itself right? Is this straight line itself right? But this straight line, one is negative one is minus one. From the left is always minus one. From the right is always one. So the two number cannot converge. So how do we write this down? Okay, how do we write this down? So we split, let's say we converge to zero in two ways. So if I mean there's this plane, okay. So we want to study the function of sequence. Consider the secant fx minus f0 and s minus 0. Okay, consider this guy. Okay, consider this guy. So if x is greater than 0, what happened? Then this guy is what? Would be, so this guy is what? This is absolute value of x minus 0 over x, right? But when x is greater than 0, it is just x over x, which is just 1. And then if x is less than 0, what happens? You get minus x over x, which is equals to minus 1. So if you take limit x to 0, okay, from the left-hand side of this function, secant function, you will always get minus 1. But if you take it from the right hand side, you will also get 1. Okay, so these are two subsequences that doesn't converge to the same limit. Okay, so that is the limit of fx minus f0 over x minus 0 does not exist. Okay. Hey, this one is cleaner, you know. This one is cleaner because why? If you are learning from calculus, right, you only learn left limit, right limit. Okay. But when we learn sequence, we look at every sequence that converge to 0. In particular, this left limit, right limit is one of such kind of sequence that converge to 0. You get what I mean? Does it make sense? Okay or not? Okay. So whenever you see limit, right, you need to replace this definition into the sequence definition. So for every Sn that converge to 0, okay, you want to look at this guy converge to what? Okay, because for every Sn that converge to 0, you also can get a sequence of this guy. You can sub Fsn minus F0 over Sn minus 0. So it's a sequence. Does it make sense? Okay, no. Okay. Okay. All right. So we can see that this doesn't exist. If this doesn't exist, then f is not differentiable at 0. Okay. Yeah. Any question? Any question? Yes. Y minus 1 minus 1 sequence. Oh, you mean you want to like go here, go here, go here, go here, go here, go here. Can a bit troublesome. A bit troublesome because you need to construct this your sequence. You need to construct your Sn. So okay, again, I think we can try and explore that. We try to be a bit relaxed today. So you can construct that. So how do you construct that actually? Let me think. You can do it in one way. So you can do it in construct a sequence xn to 0 such that limit of such that this sequence here does not converge, right? Okay, this is your job. Okay, so you need to create a sequence that converges to 0, but the secant sequence does not converge. Okay. So you want to create one sequence that is jump here, jump there, jump here, jump there, right? Jump here, jump here, jump here, jump here. Okay, so we take a very easier approach to do it, right? You see. This is the point here. You want a sequence that converges to 0, but you want a sequence that jump around 0 also. So one sequence, you know there's one sequence that converges to 0. What's the sequence that converges to 0 on n? When n large. 1 over n. This is the very first sequence we talk about that converges to 0. 1 over n. But 1 over n stays here. So you want to make 1 over n jump or how? Multiply by minus 1 to the power n. So you consider Sn to be, so let me put here. So you define xn to be minus 1 to the power n 1 over n. Okay or not? So once you pick this, your sequence is like 1 is here. Okay, sorry, minus 1 is here, half is here, 1/3 is here. So then you need to argue, if I put this inside here, I can find two subsequence that converge, but converge to a different number. Make sense or not? Does it make sense? Either converge to two limit or either diverges also can, because you want to show the limit doesn't exist. Okay. Yeah, doesn't exist have few cases, ma. Either it either it what? Either it diverge to infinity or diverge to negative infinity or just normally diverge. So normally diverge meaning did we define that? I don't think we defined that, right? We just define diverges to infinity, diverges to infinity, to negative infinity, and then yeah, that's all. And then the other situation is it doesn't converge. So if it doesn't converge, maybe you could have a subsequence that it might have a convergent subsequence, but if you can find there are two subsequences that converge to different limit, then definitely your sequence can converge. Because every convergent sequence, for every convergent sequence, every subsequence converges. So if you use contrapositive, then you can find that the origin sequence doesn't converge. Okay or not? Okay. So from this sequence, you can abstract two convergence subsequence that converge to different limit. Does it make sense? Okay or not? Any question? No question? No question. So you see, you see this calculation here is very similar to your calculus calculation. But what's difference here? When we do this limit, right, at the back in your mind, you are thinking of this kind of sequence problem. Make sense? Make sense or not? Okay, you need to think about this kind of sequence problem in your mind. Otherwise, your mindset is just stuck at calculus 1. Make sense? So when we talk about limits, quickly think back the definition of sequence. Does it make sense? So meaning I want you to recall what is the limit definition. What is the definition of limit? So let me quickly recall. Let me quickly recall. What's the definition of limit? Let me quickly recall. Today we can be a bit slow because you guys want this. Okay, what's the definition of limit of a function in terms of sequence? I think we almost reach. Yes, this one. You see? So you need to take for whenever every sequence Sn converge to X, everyone left, from right, from left, right, also can. Then Fsn have to converge to L. So whenever you see this, you need to remember this line. Okay, so what Zheng Kan did just now is I found one because you want to prove negation, doesn't exist, right? This one for every, so you need to find that exists one convergence sequence Sn to C, but Fsn doesn't converge to F. Okay, so it become a sequence question already. So we go back to previous chapter of sequence. Okay, just that in this case, we look at a specific fx, which is the secant. Again, a special function secant. That's all. Okay, make sense? Okay, so to prove you already learned university maths, whenever you see limit, you need to think about sequence. Okay. After you think about sequence, then you go to the advanced level, which is what? We prove that there's an equivalent definition between sequential definition and delta. In this case, delta n. Okay. Yeah, delta. Oh, sorry. Delta epsilon. Yes, correct. Epsilon delta. Yes, yes. Epsilon delta. Yes. So let me go to that definition. So remember this definition, and let me bring it down. So this is the definition of this is the definition what I always quote it as let me put it here. I always quote this as epsilon n definition, which is the sequential definition. because we use sequence to define it. And this is equivalent to epsilon delta definition. So let me bring this down. I can't stress enough the equivalence between these two. Wait. Here, this one. Okay, so let me make one more slide and then I put them side by side. Because they are the same, right? So let them sit together. See? Okay, so these two define the same limit L. Okay, but the second one is the epsilon delta definition. So let me name it here. So epsilon delta. Okay. So what's the difference here? The difference in the second part, there's no sequence already. No sequence. Then how? Where are the x from? So the x is coming from the range of delta. Okay, when it is delta close to C. Okay. Previously is the for large n, it will be close to C. But here I use delta to take care points around me. Previously I use n, large n, it will converge to me. But here I use delta, small delta, to control all the point around C. But at the point, but this line here is similar. Okay, you want to make sure that f of those s minus your limit is less than epsilon. Previously also less than epsilon, the difference. Okay or not? Okay, so the difference here is there might be no sequence already. Okay, to control this point. You just use a distance delta to control the point beside you. But the previously, how to control point beside you? You take large n. Right? N large enough, you are close to me. But here, I straight away what? I straight away fix a delta region. Okay, to talk about those. Does it make sense? Okay, so the task I gave you is to prove the equivalence between these two. Okay, so what I claim is the proving this equivalence is similar to proving equivalence of epsilon n continuity and epsilon delta continuity. Okay, you should refer to that proof and then prove this one. It's the same. Okay, remember what's the difference between epsilon delta limit and epsilon delta continuity? Remember what's the difference? What's the difference between epsilon delta limit and epsilon delta continuity? Only this part here. When we consider limit, I don't care the exact point at C. And when I care about continuity, I need to care about the point at C. But when I care about limit, I don't care about point at C. This is the whole point we're doing derivative, right? If we consider the point at C, what happened? And define all the second function, then you will never get something useful. But exactly because of this greater than 0, we get something useful for the derivative. Make sense or not? Okay, otherwise I'm not useful. Undefined or with. Okay? Okay. Make sense? What time is it? 4:04. We still got some more time. Okay, so let's deduce one very, I think, obvious before we take a break. So, how to relate differentiable and continuity? If you remember some facts before. How to relate differentiable function and continuous function? Any idea? If f is differentiable at x, then f is continuous at x. Hey, I remember I made you guys prove in calculus 2 and this thing. You forgot? That time we proved a multi-variable one. Use the tangent plan thingy. I think I remember. Okay, so So how to prove this? How to prove this? What do you need to do to prove a function is continuous? So suppose Sn converges to S0, right? We want to show that Fxn also converges to Fx0. Okay, so this is what we have. But differentiable is more stronger. What do I mean by stronger? If Xn converges to S0, what does differentiability tells you? The secant function, differentiability. Okay. The secant function, what does the secant function do? This limit exists, right? This converges to something which we call f prime as not. Okay. So this converges. Is this good or not? Is this good? Enough? Right? Is this good enough? Macam no, not like that, not like that, not like that, not like that, not like that. No, not like that, not like that, not like that. How we deduce the property of convergence sequence is the upper one converge, lower one converge, only the quotient converge. We didn't say the quotient converge and then the upper one, lower one have to converge. Oh. It's different. It's different. Don't use the wrong way. Only one direction. Is the upper one converge, lower one converge, and then the quotient converge. It's not the other way around. Okay. So how are we gonna use this fact to prove Fn is converged to F0? We can do some trick, right? Not that. What is Fx0, Fxn? Analysis like this trick a lot. 无中生有. Okay. So how do 无中生有? Fxn equals to minus Fx0 plus Fx0. Okay. And then, what else we can do? 现在生出一个零嘛，对不对？我会生出一个一。这个东西跟这个东西蛮像了，对不对？差了什么东西？差了什么东西？差了这个东西，对不对？有吗？说你要把这个东西变出来，是不是？你就要还一些东西给人家嘛，对不对？所以你要还什么东西 ？Yeah. So you multiply by a 1. Make sense? Okay or not? Okay. So now, instead of asking a sequence of Fsn, ask the sequence of this whole thing here. Where does this converge? If I have Sn converge to 0, this is a sequence, right? This guy converge to where? Sorry, if Sn converge to S0, this guy converge to where? 0? Correct or not? Because this is a sequence converge to 0, and then this is a constant sequence, and then the difference of this limit will be S0 minus S0. How about this one? Converge to where? F prime, X naught. Okay, so let me put here by what? By limit law of sequence, what do we get? The first term converge to F prime X naught 0. The second term converge to s0 minus x0. The last term converge to where? Just the constant term. And then all together you get what? fx0, which is what we want. Okay, we have proved that fxn converge to fx0. Does it make sense? Make sense or not? Okay, ma? Okay, yeah, so you see, what we all use here is what we have learned already. Okay, just what we have learned. Just we look at different function, the limit of different function, the limit of different sequence, special sequence, okay, which is the secant. Okay. Okay. Okay, before we break, let me tell you one secret. 我告诉你一个小秘密。喜欢听小秘密吗？有没有人想知道为什么有时候忽然间我会讲华语的？啊，不是，当我讲华语的时候，就是我要吸引你的注意的时候。所以当我讲华语的时候，尽量听我在讲，因为我要讲一个很重要的东西。OK，因为你知道为什么要这样吗？我之前一开始教书的时候，我 try 要讲英文嘛，我讲了很多很重要的东西哦，那学生全部不知道啊，所以后来我发现了，我记得如果我要讲重要的东西的时候，不是我要华语讲一遍，这样他才会懂，明白吗？OK 吗？适应，懂我在讲吗？OK，所以我讲华语的时候至少抬个头，OK，OK，给一个反应，OK，不然我不知道你懂还是不懂，对不对？你看，OK 啊，Yeah，so I think we can take a break. 我们可以继续闲聊，but let's take a break. 就take a break until 10:02。确实华语会比较好表达，你知道怎样吗？我跟我的同学啊，我们两个一起做 PhD 嘛，他也是马来西亚的华人嘛，他是槟城人。然后你知道我们怎样讨论数学吗？我们就是讲华语 mix 一些英文的专有名词，在大学的办公室里面吧，就 open space 哦。你要想啊，那些阿嬷这样走来走去，走来走去，走来走去，然后我们两个就在那边讲数学，然后掺一点华语。然后你要知道哦，我们里面也有中国人，中国人的华语有口音的，所以我们而且那里的中国老师是那种很老的，所以那种口音特别重的，不知道是东北啊还是哪里北方还是哪里的，他听不懂我们的中文，我们也不是很听得懂他的中文那种，所以他不知道我们在讲中文，你知道吗？然后讲 Are you speaking Malay？因为他知道我们从马来西亚来的嘛，所以他以为是那个马来西亚的语言，你知道吗？很多是这样的，很多那些中国人就会觉得我们的华语啊，我们明明是在讲华语哦，和马来西亚人、华人对方讲华语，他讲啊，这是你们的语言吗？那边的语言？没有啦，没有什么歧视还是什么，只是告诉你一个小趣味啊，这种故事。等你去到外面呢，国际的时候啊，就很多这种趣味发生。嗯，我感觉这里的中国学生还好啊，因为你们应该比较融入了，对不对？比较知道这里的本地话叫 pattern 啊，这里的花样，会吗？很广东口音，对对对，比较难翻哦，对，比较难翻，确实比较难翻，对，因为还没有出国前啊，我们以为中国人就只有那种福建人啊、福州人啊、客家人啊、广东人，就这种人罢了。就 I mean 不知道有别种不同的人啊，就是说北方，因为北方的人这确实会跟南方人不一样，嗯，他们的口音啊，他们的用词啊，他们的习惯全部都不一样。因为南方人喜欢吃饭，北方人喜欢吃面，都有吗？偏喜欢吃面啊，我的朋友，东北什么大米，是咩？ 可是我看我朋友哦，他们都是吃面哦，喜欢面食啊，然后对对对，还有他们吃饺子哦，然后我们吃汤圆这样，元宵节啊，中秋的时候，然后是这样哦。但是我们还是一起过啊，一起过。我煮我的汤圆给你吃，你做你的饺子给我吃哦，
那你是见过那种咸的汤圆？
咸的汤圆。
接受不了。
有啊，我有啊。那个没有，那个没有。我们是，
我接受不了那种甜。
我没有吃过。哎，是哎，他们是甜粽哎，他们放红枣，红枣，红枣。
我家是甜粽，就没有味道的那种，把那个拌哦。
哦，你是高松的。
然后再整只烧。
哎，有，也是啊，他们就是这样，他们就是这样。那是客家吗？哦，OK，呀，东北哦，他们放，呀，他们吃甜粽，他们没有，好像没有吃过咸粽哎，没有吃过咸粽啊。
咸跟甜菜
原来如此。呀，
又放
很有趣啦，很有趣，很有趣，很有趣。哦，记得有一天啊，我跟那个我同学在中国电子饭嘛，在我们那边一直聊那个数学，又讲华语讲语，然后旁边有一桌那个中国家庭一直盯着我们，在讲什么鬼？他们好像我们听得懂又听不懂。
老师，你成功研发做 communicative 的海内吗？
很搞笑。我那朋友现在在法国，
我就是那个我会找资的。
那里，所以找资料是一个 skill，一定要学的，从小就要练啊，抄东西啊，抄功课。不要讲抄功课，我们
不然就会有
参考，OK，参考。
不然就会有
怎么样？彼得抓你们，
抓他了，
抓到了啊！
他讲还找不到孔明光，
有些怎么？
讲了吧，这些东西
很有意思，很有意思。
做东西是，
对，
像我之前学那个电条一样，就是老师都不给我们知道那个白的文章是一个break 的嘛，对不对？然后他讲我不可以给你们知道那个，像跟我们玩两个游戏，这游戏是这样的，你选的号哦，我选一个号码，然后你跟我选到的号码一样，
对，
那我们就可以同时拿一个牌，比如啊，这样就好。如果选的不一样，就两个人不签啊。看了，我选74，然后你选1，这样按中的你讲你还那是前4，你去看。
你怎么知道他是按中跟你讲？
明显啊，对，因为那个游戏是你要选到跟他一样，然后他已经跟你讲选题的时候，你会选什么？下面就要跟一样，他就是换了一个方法，就这个讲应该还是那这个是第一个啊，他应该是知道我们吵的，然后看不懂啊，我还以为是好像解释那个最后一题的东西啊，然后哎呦，他只那个东西啊，只有在我们几个人有啊，其他人没有啊，一模一样，学号也是我们几个人。
那这个 Can you help me to find the whole graph？
是那个什么，direct graph，就是一个点一个点去啊，每个什么，对吧？你要去完整，这个是一个3个，他找到这3个抄，他不想再找其他，叫你们去完整，让他知道是。
对，后来
用他直接
笔记
个人不一定常驻，但那两个人一定要常驻。
哇哇，
一场我真看很久。
接着呢，
也都很
我也是对，
不过他们
很不看好的，
所以那个没有不看你们好的
啊，
一份海报哦，
没有，他们要讲可能
开
我们超太
好听点的海报，蓝地的同一期。
讨论讨论
那个
就我们讨论是，就跟他讲哦，这边来，他听了
跟我讲，你们之间如果来讨论了解不够立法的话，
我觉得应该不会，
可以，
跟
对，
就他写到这样是因为完全应该是完全一样的功能，
是一样的。
啊，算的题几乎都是这样的。
对啊，可能你看我们全部东西都一样。
这很伤啊！那个就是我抓抄的点嘛。你对的话也是我也，对呀，错我就知道。
你写
反正大点，不能换。
错的话，他写哪里错都是一样写，所以就
Hello, testing. Okay. Okay. Next. Okay, so next, so property of is of differentiable function. Okay, so suppose we have two differentiable, what can you do? We come again this kind of operation. Suppose f and g are differentiable at x naught. What can we do? Two things. What can we do? Yes, we use limit law. We can sum them to prove that f plus g is also differentiable at s naught, and then f minus g is differentiable. Sure, can, also can. Do we want to write it out? Maybe we just make it into the sum. Okay. And then what else? F times g is differentiable. What is the definition then? What is the formula? If s times g is differentiable, you know what's the formula? F times g prime plus f prime s naught times g prime. What is this? What is this called? Sorry, times g. What is this called? Product rule? Hey, product rule. And then what else? Let's say I differentiate 1 over g prime. Yeah, put outside. So this guy is also differentiable. What's this formula? Sorry? Is it possible? It could be 0, right? So we need to make it non-zero. at G, 1 over G prime. So wait, let me see. So how do we fix it? So let's see how we fix this. It could be. So we don't want it to be. So how do we fix this? Where Gx is not. So okay, where x0 is not 0 for all x in where then? In I such that this I contain S0. Does it make sense? So you got a interval such that around S0 such that all the points there fx is not equal to 0. Including x0 is not 0, gx0 is not 0. So what is this? This formula here. Quotient rule. What's the quotient rule? It's quotient rule. uv prime equals to vu prime minus u prime v over v squared. So, but here is u is 1, so minus g prime s0 over gx0 square. Okay, only from here you can deduce our quotient rule. Okay, so you can deduce our quotient rule that can I be a bit lazy? Okay, let's put it like this first. So this is differentiable at x0 as well. And then similarly, you need to mention that gx cannot be 0 for all x in I that I contain x0. Then this is our famous, if you differentiate f over g, this is our famous quotient rule. Okay, so you see that this is in this kind of sequence. So actually you get the first one first, and then you should combine with the previous result to get the last result here. So, I mean, how to prove this? What does this mean? How to prove this? Let's say, okay, I mean, I guess f plus g is differentiable. It's quite easy, right? Like Zheng Kan said just now. You just look at the limit, convergent limit of two differentiable function, right? The two secant converge, and then if you look at the sum of the two secants, then also converge. But this one is a bit special here. I give out the formula for fg prime here. Okay. Of course, we know that if the secant function for f and secant function for g converges, the product also converges, right? Because this is a limit law for limits. But how to give out this definition, this formula here? How to give this formula? So maybe let's discuss about how to get this formula. So how to get this formula here? What do you mean by definition? So yes, it is from definition, but so let's see. So since limit of so let's write it down, okay? So let's write down for this one clearly, and then the other I left you for exercise. So suppose limit of x to s0 of f x minus f x0 over x minus x0 as is, right? This one we call it f prime x0, and then also for g also exists because by what? By assumption, right? By assumption, these two numbers exist. G. Okay, so these two exist by assumption. Okay, but the question asks about what? Fg. So want to show what? Want to show the limit of x to x naught of fg of x minus fg x naught over x minus x naught exists. Okay, not only exists, and this number here equal to the formula, your famous product rule formula here, actually equal to this guy. Yeah, not only exists, and also this number here equal to the famous product rule. Does it make sense? Make sense or not? Before proving it, does it make sense? Does it make sense to you? Before proving it, does it make sense? Because you need to converge to one number, right? Is the combination of these four things number or not? Fs naught is the number, evaluate at S naught. G prime S naught is the differentiability that gave you a number, plus F prime S naught another number from differentiability of F. And then G S naught is just evaluate G at S naught. Okay, so it's a number. So why is this the number of the limit of the secant? This is the question. All right. So this is the question. So there are two things to show here. Right, two things to show here. So I've claimed that the first one should follow from what we had. You agree or not? You agree? I think don't agree, right? It's not just multiply. So I think let's prove the first one. So what about the first one? Okay, so we are looking at fg x minus fg x naught over x minus x naught. Okay, what is this? What is this guy here? What does this equal to? What is the product function? What does product function define? How to evaluate a product function at a point? How to evaluate a product function on a point? Fx gx, okay, fx gx minus fx naught gx naught over x minus x naught. Okay. And how far are we from this term here? So you see, this term is suggesting something. This term is suggesting that this secant here will converge to here. Okay. So how far are we different from this guy? So how far different? Yeah, how far different? So again, we want to play a game called 无中生有. Okay. So what to send here? What is what is worth to put in here? What is worth to put in here? So not that you see you want to introduce this G prime in, you need to introduce F prime in, but where does this G prime and F prime come from? They come from this two secants here. So you need to somehow create these two secants. Okay. So you need to take a difference between fx and fx naught and gx and gx naught. But here, fx, gx together, fx naught, gx naught together. So how I pull this fx naught out, or I want to pull the gx out. Okay, so what can we do here? What can we introduce here? Maybe we can introduce fx naught time gx, right? And then n minus Okay, so after that, what can we do here? We can split into two sum, okay, by factoring out, let's say I factor out gx on this side, and then I get fx minus fx naught over x minus x naught, okay, plus here on the other side, what do I get? Fx naught times gx minus gx naught over x minus x naught. Okay. So what do we do here? Remember, what's the condition we had? What do we condition we had? We don't just look at this secant function, right? We look at the limit. Okay, we look at the limit of this secant function. So we look at limit is what? X going to x naught of this whole thing here. Okay, but what do we know about the limit of this whole thing here? We know that this limit here converge. This one, this one is a constant number. That's fine. Gx converge or not? Why? Yeah, G is differentiable, G is continuous. So G is continuous, I can evaluate the limit x to s naught of Gx, which is Gs. So this part uses continuity. Okay, differentiability implies continuity. This part is the secant function because it's the differentiability. So altogether, by the limit law for function, we get f prime x naught times Gx naught plus fx naught times G prime x naught. Okay. Okay or not? So this is how your product rule comes out. Okay, so this is how your product rule comes out. By the way, I want to give you a heads up. And even though you see my working in the class is a bit, how to say, I would say unorganized. But this is like I want to present you the way of thinking. But when you write in assignment, please don't write like this. How you should write in assignment? Read my lecture notes. You have to read my lecture notes. You can compare my lecture notes and my Blackboard notes. They are different. Because when I teach you, I need to teach you the way of thinking. But write it out is different thing. Okay or not? Because a bit headache when I see your assignment. Because you write this kind of thing to me. I understand what you are trying to do. Okay, I understand. But when you do assignment, right, you need to write it in a proper way. Like I write my lecture notes. Did you guys read my lecture notes or not? Okay, step by step. It's not like this like random thing. I do it in class because I would need to show you the way of thinking. But when you present it, it's different thing, you know. Can get what I say? Can get Please take care. Your proof style I will start deducting mark next time. Starting next assignment. Okay, I'll deduct marks if you don't write your assumption properly. You don't how to say? So random argument everywhere. This arrow come here, that arrow come here. A lot of arrow I cannot follow. Too many arrow. Okay. So that one is your working. Okay, you write that out. Okay, and then copy to a new page. Write properly, step by step. This one to this one, this one to that one. Okay or not? Does it make sense? Cannot. Yeah, cannot. You can draw diagram, but you cannot use your diagram as your main proof.
Separate lemma and merge them.
Yes, but in the proper, okay. One thing you can do for that kind of presentation is you assume your lemma is correct first in your proof, and then after that proof, you put lemma at the bottom. This is like how I present my lecture notes, right? You see. So the one important thing, please read my lecture notes. I know some of you didn't read. So you see how I do my lecture notes. Let me see. Okay, wait, let me see. Yeah, for example, this one here. Okay, for example, I want to prove this. Okay, intermediate value theorem. Okay, I prove, and then one step here, therefore. I feel like this therefore is not direct. So I put a lemma here. I prove lemma afterward. Because if I put this whole thing inside this proof, a bit awkward. The tempo change, because this is an extra stuff. It's not quite related to the FYN here. This is just some result on sequence only. So this kind of thing I would leave out. Okay, I prove it later for you. Does it make sense? Make sense or not? Yeah, something like that. Yes. Usually this kind of small result, right? We should have done it in lectures or tutorial where you can just cite it. Therefore, by tutorial question 1 or blah, 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 or therefore by a lecture notes proposition, blah, 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 blah. If not, you want a new result, okay, go and prove it. Prove it here. Okay, extra one. But don't put this lemma inside your proof. Because this, you can see that this lemma here doesn't have anything to do with F1. Doesn't have anything to do with function. It's just some small result about sequence only. Okay. So you want to explain it clearer, then you need to put extra lemma. Does it make sense? Okay or not? Of course, when you think, right, like what you say, when the way of thinking is like I got this lemma, I combine them, and then I got the thing. But when you present it, you need to do it step by step. Okay or not? You get what I mean? This is also how you read the textbook also. They also do it in this way. Okay. Either they prove it first and then they use it later, or they use it first and then they prove it in the appendix. Because maybe it's too troublesome. Maybe you need extra knowledge. Something like that. If you put inside the main text, you'll see like very weird, different tempo. Okay or not? Does it make sense? Okay, try to learn to write a proper proof. Okay. Yeah, this will help you to read also. You will know why people write like that. Okay. So yeah. Okay, so I proved to you this product rule. So I left the quotient rule for you for exercise. Okay, the same way to do it. Product rule. What else? Let me see. Maybe something we can just skip. I just put inside the lecture notes. Not very important. A bit trivial. Hey, any one of you read my lecture notes or not? Can I have a hand? Recent lecture notes, recent one. 最近的有没有？最近都没有。哪里？哦，11还蛮近的，11还蛮近的。12、13、12、13、12、13、11、12、13呢？会感觉到比较长嘛？还好啊，还可以。因为为什么？因为我们现在到一半了我们的讲的速度会比较快，所以我很多细节在讲的时候会略过，我把那个细节放在 notes 里面 ，OK 吗？合理吗？合理啊 ，OK， 所以可能有时候你会读多一点细节在书里面，然后我好像没有讲到这么清楚，我只是一句带过吧，在班上吧 ，OK， 所以那个细节也是很重要 ，OK 吗？呀，因为我们不能够一直带，每一个都带 ，OK 吗 ？OK 啊，不然会很闷，会闷吗？我是觉得蛮闷的啦，会闷因为一直讲一样的东西嘛。不知道你们如果一直做同样东西，你们会闷吗？会吗？我也是会。所以我们尽量不要一直做一样的东西，我们要有一点新鲜感。睡觉。睡觉会OK， 睡觉是挺重要的，一定要睡，一定要睡，一定要睡。OK，几点了？10:25。Should we continue? Let me think. Yeah, so far, okay or not? you can accept。想要不要丢新概念出来？可以啊。OK， 你有力，我也有力。OK， 你们就是我最大的动力。如果学生没有力啊，我很 back 对不对？OK， 好，没问题。来接力。OK， so yeah, so let's discuss about this inverse function. Okay, how about differentiability for inverse function? So yesterday we just talked about one way to get inverse function. Where do we start? We start with a strictly monotone function. Strictly monotone function means what? Either strictly increasing or strictly decreasing. So you should think like this. So there's no staircase anymore. Okay, strictly. So why is it good about this strictly monotone function? The function is what? For strictly monotone function, the function is what? Is what? Yes, it's 1-to-1. Okay, it's 1-to-1. What does 1-to-1 mean? 1-to-1 means what? For every y in the image, there exists only one pre-image. Okay, so there exists only one x. Let's say this inverse function from where to where? Let's fix from some interval to r. Okay, interval. So okay, let's call it df only. Let's call it a domain of f. So there exists a unique x such that fx equals to y. So why is this good? Why is this good? For any one y, I got only one x. Then I can form a function backward. Okay, so we can form f inverse from fd f to, let's say, okay. So how do we do this? We take one y here and then we send it to x. Does this enough or not? Can I say like this? Can I define my map like this? Why? No. If I write the map like this, do I define a map or not? Do I define a map like this? Why? No. I mean, 这个没有意思。y 跟 x 什么关系？没有关系的。什么叫做 y 送去 x？ 如果我给你2，那你送去哪里？送去 x， 什么叫做 x？ 送去1。3呢？也送去1。所以什么 x 来的这个 x 跟 y 什么关系 ？Such that what？ Such that fx equals to y。所以这一个 fx equals to y 告诉你了这个 x 跟 y 什么关系？为什么？为什么？因为你要送去的地方是要是 f apply 过后你拿到 y 的，你才可以 check。你有 f， 你有 f 有 y， 这样我就可以 check 了咯，这个 x。但是之前什么都没有，什么叫做 y 送去 x？ Okay, so here such that fx equal to y, then we have a way to check whether this x is the x we want or not. But why this condition is enough? Why this condition is enough? To define a function. Yes, because f is 1-to-1. Because there's only one guy can satisfy this. If two guys can satisfy that, let's say x1 works, x2 also works, then y have to go to x1 or x2. Cannot, my function cannot do that. Okay, so that's why from 1 to 1 you can define a inverse. Okay. Okay, so this is about inverse. And then so we can look at this kind of function. So let's look at this kind of function example. Let's say we look at this kind of function. Let's say increasing, strictly increasing. Say this kind of function. Strictly increasing. Then so just now, let's say this function is differentiable. Okay, let's say it is differentiable at this point as not here. So that means we can find a limit of secants, and then we can make the tangent line here. Okay. So this is a function from x to y, say. Okay. So this is a strictly monotone, strictly increase. Okay, assume differentiable, and then continuous, definitely. So let's call this f. How does f inverse look like? How? 宽爷，好，对称回去，怎么对称法？怎么对称 ？You mean 对称 around y equal to x? Is it what you mean? So let's say y equal to x is here, right? And then you form a opposite one, something like this. Right. Like this. That's what I mean. True or not? Is it true? Is this a f inverse? You believe so? Yeah. Okay. Actually, there's another way to see it. So there's another way to see it. So let me copy this. Copy, 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 copy. And paste. Actually, there's another way to see this. Okay, let me get rid of the normal one. What I do, I just simply swap y and x. Huh? Also works, right? Think about it. Think about it. Previously, we have x, give you one x, you give me one y. Okay, but now you give me one y, I give you one x. Make sense or not? Does it make sense? Okay, so you give me one y. Oh yeah, you give me one y. So let's say this is a y naught. You give me one x naught. Okay, where this y naught is actually equal to fx naught. Make sense or not? So it's really the same graph, just depending you're swapping the domain here. So if I want to look at this f inverse here, the gradient at y naught. Okay, the gradient at y naught. What do you think the gradient should be? What's the gradient should be? What do you mean by so? Yeah, right. What kind of swap is that? There's a few swapping in the max. So what kind of swap is that? Yeah, so that is you taking the inverse. You're taking inverse. But you see, the tangent line is really same line or not? Is it the same? Not quite same. Is it the same? Huh? Is it the same line? Is it the same tangent line or not? No. No. Yeah, it's not exactly the same tangent line, but the gradient is the inverse of each other. Right or not? Okay. So how are we gonna prove that? Uh-huh. We take the secant function of so let us just quickly work it out informally. So we take a secant function of f inverse of y minus f inverse of y naught. Let's say y over y naught. Right or not? So this is a secant function here, right? Okay. But what is this? What is the inverse of y? What is the inverse of y at y naught? You should know the inverse of y naught, right? What is that? S naught. Correct. And then inverse of y, maybe we call it x. Just call it some x. And then the bottom, y minus y naught. Let's say this x is the one that give you fx. This is the x that give you y. Okay. And then y naught is equal to f x naught. But what is this? 1 over fx minus x naught over x minus x naught. So what do? If you want to compute the limit, you compute the limit of the whole thing here, right? So here become a limit from what to what? From fx naught fx to f of x naught. Is this correct or not? Let me see. Is this correct? Look a bit weird, but is it correct? Okay. So I mean, just now we want to have a goal that this reach to, does this reach to 1 over f prime of x naught? Okay, if to reach to this, right, then we should have a limit from x to x naught. Okay, but do we have that or not? Continuity. I think definitely we need somewhere. Let's think about it. So how? Well, I think we need somewhere. We need the continuity to come in. So how do we introduce the continuity? So how do we go from this limit fs to fs not going to s to s naught? Okay, so this is our problem. Okay, so we need to require proof here. So this is like we need a lemma here. For a lemma here. So if limit of okay, I think we should write this. If fx converge to fx naught, then x converge to x naught. Okay, we need to prove this. So how to prove this? Inverse exists for x. What do you mean? What do you mean? Mm-hmm. Mm-hmm. Say again. Uh-huh. Uh-huh. Oh. Oh yeah. Sure. Yes. I think you are right. Okay, very good. So I think you're right. Good. So what is the proof here? So suppose Fs converge to Fs naught. Okay, so what does this mean here? Okay, do we want to use sequence to talk about it? So let's use sequence to talk about it. So let's do it in the pretty good detail. So suppose this converges, this means what? I think we don't need to go into epsilon delta. Let's stay away a bit first. So meaning for every Sn converge to x0, we have what? Fxn converge to n0, Fn0. Does it sound a bit circular? Does it sound a bit circular? Doesn't look not circular, right? We start with something that converges to that thing. Let me think. Oh, okay. I think I know what's the point. Wait. Let me think. Let me think again. So, what is this here? Suppose X converge. I think something is not precise here. Yeah, we definitely want to introduce inverse, but I think there's some weird thing. So, what's the weird thing here? Because here Sn converge to S0, right? Top there I say S converge to S0. So what does that mean? P of X is going to 0. So it is the identity function. I think, okay, I think I should say here is the identity function X going to X naught. Is better, is it? Well, what does it mean by S converge to S naught? I think there's nothing to mean, no meaning there. S converge to X naught. Fx converge to X naught, we have a definition. But S converge to X naught, there's no definition. Huh? Yeah, it's equivalent to that. Wait. Yeah, it is equivalent, but I was trying to like write down this claim here. Is this claim looks weird or not? What do I mean? What do I want to do here? Okay, let me write in the other way. So let me rephrase this. Let me rephrase this lemma here. Let me rephrase this lemma. So what do we want to have? So rephrase this lemma. So we want to prove that let's see whether we want this or not. So if we have this fx naught, then limit of x is equals to x naught. Yeah, I think this sentence refer to the identity function here. Otherwise, doesn't quite make sense. Yeah. Yeah. So if x inverse is continuous or not, okay. So this question here, do we assume it is continuous? Let me think. Actually, we assume f is differentiable. So let me think. If f is differentiable, then we want to prove that f inverse is differentiable. We want to prove that f inverse is differentiable. So, okay. So let's put let's write down what do we have here. Okay, so what's the condition we had here? Okay, so what is the condition we had here? So let f df to r to be strictly monotone. Okay, because we want to define the inverse. Or if you like, we can start with injective. Okay, you can replace this one with injective function. And we want f to be continuous also. Then, suppose f is differentiable at our point s0. Okay, and of course, f prime x0 is not equal to 0. Okay, then what do we do? Then our claim here is f inverse of fd to r is differentiable. And differentiable at y0, which is fx0, and the derivative is exactly the derivative at y0 is exactly 1 over x. Okay, this is what we want to do here. So we want to prove that f inverse is differentiable. Okay, but do we know that f inverse is continuous? This is a very good question. I think yesterday we missed this. Yeah. 对，有这个 theorem， 有这个 theorem。So 这个 theorem 是说，如果 f 是strictly monotone， OK，and then 它的 inverse exists，and then 它的 inverse 应该要是 continuous。昨天好像我们 skip 掉这个 statement。Yeah， 它要是 continuous。OK，so I think yesterday we missed that. Yesterday we should say if f strictly monotone and then continuous, then f inverse is continuous. OK， 我们应该要有这个 result 先 ，OK， 才可以。OK， so let's say if we have this result already, can we continue or not? So you see this limit here, seriously, we should think about this x as an identity function. Otherwise, it's not defined because we define the limit of a function. Understand or not? Then we define a limit of a function. Okay, so here is if my fx converge to fx0, is the identity function converge to s0 also? Okay, so I think this makes more sense. Does it make more sense? I think so. Okay. Yeah. Sorry. 对 Yes. 我们要用 f minus 1那个 So how to use? 对。So 你看 so it's like this. So I have a fx0 converge to f0 means what? For every s0 converge to s0, I have fs0 converge to fsn converge to fs0. Wait. So since f inverse is continuous at fx0, then what can I do? F inverse of fs0 also converge to f inverse of fs0. 没有什么？没有 n 哪里没有 n？ 要有 n。这个没有 n。可以这样咩？Let me think. No, 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 no. So I mean, be careful. So let us be careful a bit. So what does this line mean? This line means what? This line means limit of x to x naught of fx equals to fx naught. 什么叫做加 inverse on both sides？ 然后你要加在这边，明白吗？明白我讲什么吗？懂我什么意思吗？对吗？我这个是 by OK， 这个 so this 这个只是一个 shorthand notation for 这个 limit 罢了，for 这个。OK， 什么叫做我可以直接加 inverse 在这边，对不对？加 inverse 在这边，难道我加在这边？对吗？你可以加两边是加在 sequence 上面罢了，记得吗 ？Continuity 的 definition 记得吗 ？Continuity 的 definition 还记得吗？So so 让我放这边啦。F is continuous at x naught. What does it mean? If for every Sn converge to S naught, Fxn converge to Fs naught. OK 吗？所以不要 confuse 啊，不要 confuse 啊。这个 Fx converge to S naught 啊，是一个 limit of function。limit of function， 所以我可以加在这边，其实我可以加在这边。OK， 我加在这边有什么好处？左边是什么 ？Sn， 右边是什么 ？S naught。然后我 prove 了什么？我 prove 了什么？如果我有 Sn 去到 Sn 就去到 Sn， 有点白痴的感觉。为什么感觉到有点白痴啊？想一下，我想一下为什么这个 argument 有点白痴？想一下，我已经 start with Sn convert 去 S not 了 ，and then 感觉有点白痴哦，这个 argument。You guys think a bit redundant or not？ 多余，会吗？会不会有点多余啊？这个东西，想一下，会不会有点多余？会有点多余这个 argument。你看啊，我们一开始 start from 就是 Sn convert 去 S0了，其实，有点 redundant。你们觉得呢？感觉没有错啊，没有错，但是感觉有点多余。你们觉得呢？因为为什么会多余啊？因为一开始当你要 fx convert 去 fs0的时候，其实你已经 start with 一个 Sn convert 去 S0了，所以你已经有那个 convergence。现在只是说，我们somehow忘记了这个 Sn convert 去 S0，我们只去看 fx convert 去 fx0，但是其实背后已经有 Sn convert 去 S0了。你懂吗？然后我们怎样把这个 Sn convert 去 S0找出来？我们只是 apply 一个 inverse function 把它挖出来吧。想一下，想一下，我们下一堂课那个，下一堂课应该，下一堂课可能我们会上1个小时过后，我们再考试。OK，3个小时嘛，下个拜二，我们上1个小时，我们再考试。OK。 呀，我们下次再回来想一下这个多不多余。Okay. Okay. So good luck in your statistic, huh? Statistic.